Physics Bootcamp Addendum Problem 5. Problem 5 says if the work function of a metal is 2.45 electron volts, what is the minimum frequency you must shine on it so it ejects electrons? The second part of the question says if you shine light of 3 times this minimum frequency, what is the stopping potential? Okay, so this question concerns the topic of what is known as the photoelectric effect. The photoelectric effect. This theory is what Albert Einstein got his Nobel Prize for. A lot of people think that Albert Einstein got the Nobel Prize for his theory of relativity, but in actuality it was his theory explaining the photoelectric effect, which was credited to Albert Einstein with a Nobel Prize. So the basic gist of the photoelectric effect is you have a certain metal here, and you connect a circuit to it, and the metal might be silver or something else, copper. Then you shine light of a certain frequency on it. According to classical mechanics, the intensity of this light should determine how much electrons are ejected from this metal. So the electrons are ejected from this metal, and they travel across to this other metal, and then you get a current. So if you have an ammeter, the way that you know that the electrons are have gone to the other side is to read the current here, and from the current you could determine that the electrons have been ejected and actually going around the circuit, right? So according to classical physics, the intensity of the light beam should determine how much current we get. Well, when they actually tried this with a light of a certain wavelength, let's say red light, blue light, and then they upped the intensity. By upping the intensity, what you're actually doing is you have more of the light beam, okay? In terms of quantum language, you have more photons. The light beam has more photons. Well, when they did this experiment, they found that the intensity has nothing to do with the current. As a matter of fact, at a certain frequencies, no matter how bright the light was, no electrons were ejected, the current reading was 0, okay? So what they actually found was that it was the frequency that determined the current. The frequency determined the current. Okay. For example, with certain metals, red light did not have sufficient energy. You needed more blue light or green light to have sufficient frequency and sufficient energy to eject the electrons from the metal. Okay. So that means this photoelectric effect showed that the energy of a light beam is proportional to its frequency, and the frequency is what determines if the electrons were ejected, right? So you could read up on the photoelectric effect more, understand the details of this. I'm not going to go through each piece by piece of the theory, but the basic gist of it is that the photoelectric effect proved the equation, and Einstein explained that the energy of the light beam is proportional to its frequency, hf, and h is Planck's constant, okay? And this energy of the light beam needs to be equal to at least what's known as the work function of the metal. Work function of the metal, okay, we'll just write it like that. Plus, if the frequency is even higher than that, right, then you will actually be able to eject electrons which have a certain kinetic energy, so that extra energy that the light beam has will go into the kinetic energy of the electrons. Right? And the more the kinetic energy of the electrons, the more the current reading will be. So you will have a large, huge current, right? So in this case, we are asking, so the equation of the photoelectric effect can be summed up with this equation. So in this case, we are asking the work function of the metal is 2.45 electron volts. What is the minimum necessary frequency? So what we do is we say when the kinetic energy is 0, hf is equal to the work function, 2.45 electron volts. And remember from the previous problems, that we have to convert electron volts to joules, and then we can calculate the frequency from there. So we use the Planck's constant, 6.626 times 10 to the minus 34 times frequency, and then that's equal to 2.45 electron volts, and then 1 electron volt is 1.6 times 10 to the minus 19 joule. Electron volt cancel, and of course this is joule seconds, joule cancel. 5.916 times 10 to the 14 hertz. Right? Now if we want to know what wavelength of light that corresponds to, because a lot of times we know more about wavelength than frequency, right? So we can go and say, okay, wavelength times frequency is the speed of light. So wavelength is equal to speed of light over frequency, 3 times 10 to the 8 over 5.916 times 10 to the 14. So we take the answer that we just got, we invert it, and then multiply it by 3 times 10 to the power 8. 07 times 10 to the minus 7, which is 507 nanometers. And again, to get a perspective, we compare that to the visible light range from 400 to 700. So we are closer to the 400, which means this might be appearing, remember, Roy G. Biv. 700 is a red, and then as you're going smaller wavelength, you're getting violet. So let's say for the sake of argument that this is green verging towards the blue. So let's just say green-blue. So what that means is that in order to emit electrons from a metal which has a work function of 2.45 electron volts, we need a light of minimum wavelength corresponding to a green-blue color, right? If you shine on it red, no electrons will be emitted. The current in the circuit will be 0, right? So now what's happening to the second part of the question? If you shine light 3 times this minimum frequency, well, then you're going to have sufficient energy, right? So you're going to have energy is equal to HF, which equals the work function of the metal plus the kinetic energy of the electrons. So if you have 3 times the frequency, so what does that mean? Well, then this is equal to 3 times the minimum frequency, F min, times H, equal to the work function of the metal plus the kinetic energy. And so 3F min H minus the work function of the metal equals kinetic energy. So that means the electrons will have kinetic energy equal to what? Well, what we do know is that F min times H, how did we even get F min, right? F min times H was equal to the work function, right? F min the way that we got F min was that we set F min H equals to work function, and then we got our minimum frequency, right? In order to do this kind of quicker, we can just say F min H is equal to Wm. So we have 3 Wm minus Wm equals kinetic energy. So the kinetic energy equals to 2 Wm. As a matter of fact, that ends up equaling the maximum kinetic energy. The maximum kinetic energy of the electrons. Some of the electrons won't have that kinetic energy, but that gives you the maximum that the electrons will be shot out with from the metal, right? It'll be twice the work function. So the kinetic energy of the electrons maximum, 2 times the work function. The work function is 2.45 electron volts, and that's equal to what? 4.9 electron volts. Now, if I want to stop all electron flow and I want to completely have no current in the circuit, so let's go back to the picture. I'm shining this beam of light. The electron with the most maximum kinetic energy has a kinetic energy of 4.9 electron volts, right? Some of the other electrons are like bouncing around, bouncing around, bouncing around, bouncing around, going over there, but with less kinetic energy, right? The quickest one is going there with a kinetic energy of 4.9 electron volts. If I want to stop that, what do I do? With these two metal plates on either side, I can create a potential difference, right? Electrons tend to naturally want to go towards what potential? From electricity and magnetism class, we know that electrons like to go towards higher potential naturally, right? Towards higher. So if I make this side lower potential, so let's call this Z and let's call this V, right? If I force an electron to go towards lower potential, it's actually going to slow down, right? It's gonna gain, it's like it's gaining potential energy, right? So it's kind of like taking my calculator, forcing my calculator to go up, right? Gaining potential energy. By gaining potential energy, it loses kinetic energy, right? So if the electron goes from higher to lower potential energy and the voltage is equal to V, how much potential energy does it gain? Well, notice here, the energy delta U is equal to charge of the electron times the potential final minus the potential initial. 0 minus V, right? So then what is that going to equal? The charge of the electron is negative E, and then times negative V, EV, right? So the electron gains a potential energy EV, therefore it loses kinetic energy, right? So if I fine-tune the voltage, and this is called stoppage voltage, V stoppage, if I fine-tune it, I can actually set this equal to this, right? So therefore I can say delta U is equal to kinetic energy maximum of the fastest moving electron, right? So that's equal to 4.9 electron volts, and the energy gained by the electron, therefore if that's equal to the kinetic energy of the maximum electron, that means even the fastest moving electron will stop by the time it gets there, and therefore the current in the circuit will be 0. The current in the circuit is 0. And that's how we can test the photoelectric effect. We can shine a light of a certain frequency, okay? We can raise the frequency, and then once we reach the minimum frequency, we know there's a certain current. We pass that frequency, okay? You can pass that frequency by a certain amount, then increase the voltage on the one of the plates, okay? Increase the voltage until the current is 0, okay? So what's the stoppage voltage gonna be now? EV stoppage. Well, E cancels E. This is the charge of the electron. This is also the charge of the electron, 4.9 electron volts. And so this cancels, so the stoppage voltage equal to 4.9 volts. Okay? So the stoppage voltage depends on what frequency of light I'm shining it, right? If I'm shining light of frequency less than the minimum, then I don't need a stoppage voltage, right? It's already no electrons are gonna flow. But if I shine light frequency greater than the minimum, then I need a certain stoppage voltage, okay? So now you know how to approach these kinds of problems. This is a beautiful topic called photoelectric effect, and it was one of the main important cornerstones on which quantum physics is based, okay? Thank you very much.